Okie doke. So let's start talking about Chapter 2, the chemical basis of life. Now, I know personally for me, being a biologist, chemistry is not my favorite. But in order for us to understand the processes that are going on in the body, it is very essential that you have a very basic understanding of chemistry. The chemicals that compose the structures in your body and the interactions of those chemicals with one another are responsible for how your body functions, how it works. So we're going to go through some basic chemistry together. So this is the outline of the chapter. We've got basic chemistry, chemical reactions, and energy. By the way, E with a plus is energy. If you see E with a minus, that's electron. Okay. Inorganic chemistry with water and solution concentrations, acids and bases, oxygen and carbon dioxide, and organic chemistry with carbs, lipids, proteins, nucleic acids, and ATP, I'm sorry. So let's start with basic chemistry. Matter, mass, and weight. All living and non-living things are composed of matter. So you're composed of matter, your cat, your dog, your daughter, your mom, your dad. But at the same time, the desk you're sitting at, the table you're sitting at, the glass you're using, everything is composed of matter. Matter is anything that occupies space or has mass. Now, mass is the amount of matter in an object. So that sounds like circular logic, right? Well, what's mass? It's the amount of matter. What's matter? It has mass. Okay. So mass is basically how much is there, how much stuff is there. Matter is anything. Matter could be the air. Technically, the air takes up space, right? If I fill a balloon, that space that's being filled is filled with air. When it comes to mass, our second word up here, we use the units of kilograms, okay? That's kind of our base unit. Weight is a bit different. Weight has to do with gravitational force acting on an object of a given mass. Now, I know you're going, okay, but people weigh themselves and they say there's so many kilograms. That might be true, but weight is still different. Remember, mass is how much stuff is there, right? So if I have a jar of ball bearings on Earth, it takes up the space that is that jar, right? And let's say, for the sake of argument, it weighs 5 pounds on Earth, right? So that's the weight. Mass, however, if you think about it, I can take that jar of ball bearings to the moon, right? The mass, how much space that takes up, is still the amount in the jar, right? So the mass has not changed. However, what's the gravitational pull of space? There isn't any, right? So the weight is completely different. It doesn't match up. It's kind of the same as saying my weight on Earth versus my weight on Jupiter. Jupiter has a huge amount of gravitational force pulling toward its center compared to Earth. So my weight would vary. My mass, however, would not. It wouldn't, because literally the amount of space I take up is the amount of space I take up. The amount of stuff that makes me is the amount of stuff that makes me. So yeah, that's the difference between mass and weight and matter. Now, an element. An element is the simplest type of matter with unique chemical properties, basically multiple atoms of the same kind. So I said I had a mayonnaise jar full of ball bearings, right? So the element would be the ball bearing. And the reason that I say that is because it has a spherical shape. If I take that and I cut it into anything smaller, it is no longer a ball bearing, right? So the element would be ball bearing. That's as simple as I can get that element, okay? The most common elements in our body are oxygen, carbon, hydrogen, and nitrogen. Oxygen, carbon, and hydrogen are all found in the major components that build us, our major organic components, in carbohydrates, in lipids, in proteins, and in nucleic acids, our DNA and our RNA. Nitrogen is part of protein and DNA and RNA, but not the other two. So when we talk about what's the most common chemical you see, these are the four most common, and they're represented by a symbol. I love the way they say symbol, like there's some hieroglyphic there. To us, the symbol is a letter, which technically is a symbol. Now, an example would be oxygen. Oxygen is represented by the letter O. And for the most part, we do try to kind of stick to that first letter. The thing is, there are things that repeat. For example, sulfur, sodium, selenium, all of them start with S. So what do? Well, with sodium, we changed it to Na. Now you're probably going, okay, how did you get Na from sodium? Because that was kind of my question too when I was first looking at this, going, Okay, one of the common themes that you see in science is the use of Latin. Latin is a dead language. So in Latin, sodium is called natrium. Okay? Now you might be going, why do we have to learn Latin? Okay, so let's talk about a living language versus a dead language. A dead language means that natrium will mean natrium, and if I'm in Japan, or if I'm in Zimbabwe, or if I'm in Iraq, it doesn't matter. Natrium means natrium because it's in Latin, and Latin doesn't change because it's a dead language. Think about the English language for a second. How many words mean one thing, and then we say it a different way, and all of a sudden it means something else? So, for example, and for those of you that are a little older, this might be a little confusing, but I learned it because I'm older from my younger students. Ratchet. What does ratchet mean to you? See, to me, ratchet is a tool that you take out of a toolbox and you use it to kind of take a nut and a bolt and put them together. That's ratchet to me. But in a living language, that word has taken on a whole new meaning, right? It means ghetto. So that difference in meaning, I mean, think about it. We're talking about a noun, something that actually physically exists that I can use my hands with, versus, oh my gosh, she's so ratchet. She looks so ghetto, right? That difference in language means that our language as a living language is constantly evolving. Using English in some cases just doesn't work as well as using a dead language that never changes. So natrium is sodium. Period. End of story. Because there's nobody out there going around speaking Latin. So it's kind of a stable way of giving something a moniker, giving something a name. So when we talk about elements, elements are kind of the general name for something. But if I want the smallest bit of that element that is still that element, I talk about having an atom. An atom is the smallest particle of an element that still has the chemical characteristics of that element. I kind of already mentioned this before, having a jar of ball bearings. Let's say that for the sake of argument, our element, really, can't even spell the word our element is ball bearings, right? That whole jar has them in there. But what is the smallest piece that I can take out of that jar that is still that same thing that's inside the jar? Well, I can take one of these out. and it would be 1 ball bearing, right? Well, technically, I can have a beaker full of carbon. That can happen. I can have this beaker full of carbon. But when we talk about the one piece of that that can basically be whatever is in that beaker, it's 1 atom of carbon. So again, the atom is the smallest particle of an element that still has the chemical characteristics of the element. With the ball bearing, if I try to cut this in half or cut it in quarters or anything like that, at that point, I no longer have a spherical ball that I can claim is a ball bearing because it doesn't match up anymore. It's the same with an atom. An atom has very specific properties. And if you break that down any further, it is no longer the same thing as what you have in the beaker. So, looking at the periodic table, you will notice that we have quite a few elements. The carbon I was just talking about before, right? That carbon is there. It's at position 6. Hydrogen is at position 1. Oxygen is at position 8. Helium is at position 2. And I do want you to notice that they do have really specific places where they fit. Okay? So, let's talk about an atom's structure. Okay? The characteristics of matter result from the structure and organization and behavior of atoms. You've got basically 3 subatomic particles. Atoms are made up of 3 parts. You've got neutrons, you've got protons, and you have electrons. Okay? And in an atom, you have 2 kind of locations. Dead center in the middle, you've got a nucleus. Okay? But then outside of that, out here, you've got what is called the electron cloud. Okay? So the nucleus versus the electron cloud. In the space that is the nucleus, you only have 2 subatomic particles. The neutron is in the nucleus, and the proton is in the nucleus. Okay? As well, our neutron has no charge to it. That's why it's called a neutron, because it's neutral. Our proton has 1 positive charge per proton. So for every proton, there's 1 plus associated with it. Okay? Now, the electrons. The electrons are, oddly enough, in the electron cloud. That's where we find them. And unlike our proton that's positive or our neutron that's neutral, okay, neutral, our electron has 1 negative charge per electron. So if you've got an electron, you've got a negative charge associated with it. Now, something else that's kind of interesting. The protons and the neutrons are 1 trillion times bigger than our electron. Okay? So when it comes down to size, neutrons and protons are 1 trillion times bigger. That has a lot to do with the mass that we talk about. Okay? Something else that's kind of interesting. That nucleus is kind of densely packed dead center inside of the center of an atom. And I'm sure everybody here has seen an atom drawn something like this. Yes? Okay. Kind of looks like a solar system with planets. The cloud that's around that nucleus is not that organized. There is not a specific set of orbitals that those electrons follow. What we do know is you can find the electrons in this space around the nucleus. That's what we know. Not necessarily where at any given time, just that we know that's how much space that cloud takes up. So if you look at the difference in size between where the nucleus is and where that electron cloud is, you'll notice that that electron cloud takes up a lot of space, right? It takes up a lot of space. So when we talk about the volume of an atom, most of that volume is actually that cloud space, not really the nucleus. Now, something else. In a perfect world, okay? Whoops. In a perfect world, the number of electrons, protons, and neutrons would always be equal. So if I have 10 of one, I have 10 of another, I have 10 of the last one. That's how it would be in a perfect world. Do we live in a perfect world? No. So it doesn't necessarily follow that rule, but when we're first learning, we kind of want to start at that point, and then we apply rules as we learn more. So looking at some of these periodic table squares, there we go, a little bit closer. I want you to notice that at the top of these squares, I have whole numbers. See that? But at the bottom of the squares, I've got these decimal pointed numbers. I also have my symbol, my letter, and I've got the name of the element right below that. Okay. In a perfect world, the number of everything would be equal, the number of protons, neutrons, electrons. For our purposes, actually for science purposes, it's not just for us, this number up here, this whole number up here, this is called the atomic number. Okay? The atomic number is the number of protons in each atom. And it never, ever changes. If I've got 15 protons, I have phosphorus. Period, end of story. If you change that, let's say instead I have 16, well then I don't have phosphorus anymore, I have sulfur, okay? Literally, when it comes to that whole number, 15, 16, 17, 18, you know exactly which element you're talking about because that tells you the identity of what you're looking at. Atomic number is always a whole number, and it's always going to be the number of protons that you have present. So if I give you a random proton number, you can literally look at any periodic table and tell me exactly which element I'm talking about, because atomic number is a whole solid stable number. Okay? Whoops, wrong direction. So for example, if I were to say, if I were to say number 24, you would know I'm talking about chromium. If I were to say number 46, I'm talking about palladium. How do you know? Because this number right here is the number of protons in palladium, 46. That number doesn't change if we're talking about the same element. Palladium will never have 45 protons. Palladium will never have 47 protons. If that number changes, literally the identity of the element that you're looking at also changes. Okay? So let's talk mass number. Okay, mass number is the number of protons plus the number of neutrons. Remember that protons and neutrons are a trillion times bigger than electrons. So we don't really think about electrons when we think about how much room this atom is taking up. We really can't. It would be equivalent to me going into the doctor and them saying, we need you to step on the scale, and me going, hang on, there's a flea on my shoulder. It's going to make all the difference. If I did that, I'm pretty sure they would ask for a psych consult, right? The flea doesn't really do anything to my weight. So, in a perfect world, remember what I said, the number of protons would be the same as the number of neutrons, right? In a perfect world. So if we go back to phosphorus and its proton number is 15, it should be 15 protons plus 15 neutrons equals 30 atomic units, right? If we live in a perfect world, yeah. But looking down here at the bottom, do you see how that isn't a perfect 30? It's actually 30.973762 atomic units. Yes? All right. Mass number is the penultimate perfection. Reality is something that we call atomic mass. Okay? The thing about atoms is that they are not all going to have equal numbers of anything. We do not live in a perfect world, meaning that the number of neutrons can vary. Now, remember what I said about protons. Protons cannot change. The only other thing that we have that is equivalent in size to a proton is a neutron. So it would be like me gaining or losing weight. If I lose 10 pounds, do I become a different person? No. If I gain 10 pounds, do I become a different person? No. So when I've got an atom and it's got, let's say, 15 protons plus 16 neutrons, that 15 proton number still says that that's phosphorus. That has not changed. That phosphorus is still phosphorus because I have 15 protons. I may have 15 protons and I might have 75 neutrons. Not that that really is something that you would necessarily see that isn't man-made, but let's just go with that. That 15 proton number still means that it's phosphorus, okay? So, why do I mention this? Well, I mention this because this number down here is not that perfect number 30, right? Meaning that in nature, we do see phosphorus atoms that have different numbers of neutrons. So we've got some that maybe have 16, we have some that maybe have 17, we have some that maybe have 14. We probably do have the 15-15 spread too, but that perfect number isn't a really good way of calculating things when you need to make chemicals. So when we talk about the atomic mass, this is actually an average of mass because of what we call isotopes. Iso means same. So isotopes are basically going to be the same element with different numbers of neutrons, okay? So when you've got that variation, you've got 15 protons, 16 neutrons, 15 protons, 15 neutrons, 15 protons, 14 neutrons, 15 protons, 17 neutrons. We call that an isotope because technically all of those things that I just mentioned are phosphorus. How do I know? 15 protons. If it's got 15 protons, it is nothing else. It is only ever going to be phosphorus because that's its atomic number. But The variation in the number of neutrons, we call them isotopes. And when we are trying to figure out how to use a chemical in a chemical formula, we tend to want more of an average number. We want something that is more accurate than just perfection. So when atomic masses were being calculated, they basically took all of the naturally occurring isotopes found in nature and they made an average. And this number down here, this atomic mass number, is the average mass of the isotopes we find in nature.